Hi, this is Mr. Beck from War Hill High School. In this video, we are going to apply the understanding of Lewis dot structures so that we can recognize good Lewis dot structures from bad ones. Our objectives in this presentation will be to count the total number of valence electrons that should be in a molecule. We should be able to count the total valence electrons. We also want to identify when a line structure meets or violates the octet rule. We're going to be able to count the number of lone pairs on a central atom because that's going to be important in the future for the structure of molecules. And we also want to identify when a line structure has the correct number of valence electrons. The way we're going to get there is first we're going to show you how to draw Lewis structures. We're going to give you the rules for Lewis structures to draw them for molecules as well as for polyatomic ions. And then we're going to show some examples of Lewis structures that will allow you to recognize whether they are correct or incorrectly drawn. So first, let's talk about drawing Lewis structures. There's a set of rules that we use to draw Lewis structures for molecules and for polyatomic ions. The first step is we are going to be counting the valence electrons available for bonding. And so for polyatomic ions, we're going to be adding electrons for each negative charge. The second step is we're going to connect the atoms by single bonds around a central atom. So each single bond is going to use two of those available electrons. Next, we're going to fill the outside atoms with electrons so that we can meet the octet rule. So we're going to take some of the remaining electrons and put them around the outside atoms. And remember that hydrogen can only have two electrons to begin with. So if hydrogen already is participating in a single bond, it already has all the valence electrons that it needs. Next, if we have any remaining electrons, we're going to fill the octet of the central atom. And finally, we're going to check to see if the central atom does not have a full octet. If the central atom is still lacking electrons, then we're going to have to pull in pairs from the outside atoms to form double and triple bonds as necessary. So let's take a look at some examples. For example, if we wanted to draw the Lewis structure of H2O, well, our first step is to count the valence electrons that we have available. I'm not going to worry about drawing the Lewis dot structures of each atom. I just want to know how many electrons. Well, hydrogen, I know we have two hydrogen atoms. Each hydrogen atom is going to have one valence electron because it comes from the first column of the periodic table. So two atoms at one valence electron each gives me two available valence electrons that the hydrogens bring into the molecule. For oxygen, I have one oxygen atom, and that oxygen atom is going to bring six valence electrons because oxygen is in group 16, and group 16 elements will all have six valence electrons. So with the six valence electrons from the oxygen and the two valence electrons from the two atoms of hydrogen, that gives me a total of 8 valence electrons that we can play with. So if we move on to the next step, we want to connect the atoms by single bonds around a central atom. Well, let's place oxygen in the center and then put the hydrogens around the outside. Very often, if you have one of one atom and then multiples of the other, you're going to want that single atom in the center. That's not a hard and fast rule, but it is a general idea. So we'll put the oxygen in the center and connect it to single bonds with hydrogens. Now, those single bonds, each line represents two electrons. So I've already used 4 of my valence electrons out of the total 8 that I have to use. Next, we're going to fill the outside atoms with electrons to meet the octet rule. Well, hydrogen already has 2 electrons. Each hydrogen is associated with one of those bonds, and therefore the hydrogen is already full. I can't add any more electrons to the hydrogen. So I'm going to move on to the next step because hydrogen can only have 2 electrons. So the remaining electrons I'm going to use to fill the octet around the central atom. I had used 2 4 electrons already with the bonds between the hydrogen and the oxygen, so that left me with 4 more electrons. So I'm going to put those in pairs around the central atom. So that's 5, 6, 7, 8. So you can see I've used a total of 8 electrons, and those are the 8 valence electrons that I need. The next step is if the central atom does not have a full octet, then we share lone pairs from the outside. I don't have to worry about that step in this case because I already have a full octet around the central atom. So that oxygen has 2, 4 with the single bonds with each hydrogen. That each one of those lines represents 2 electrons. So there's 2, 4, 5, 6, 7, 8. So the oxygen has a full octet. The hydrogen is happy, the oxygen is happy, and the other hydrogen is happy. So I have satisfied and I have made myself the Lewis structure for H2O. So it's a hydrogen on either side, and then the oxygen has 2 lone pairs. You'll notice that that central atom, that oxygen, has 2 lone pairs around it, and that's going to be important later on for the structure of molecules. For our next example, let's take a look at carbon dioxide, CO2. The first step is to count the valence electrons. Well, carbon comes from group 14, so it's going to have 4 valence electrons. So the one carbon atom times the 4 valence electrons is a total of 4 valence electrons that the carbon brings to the table. Next, we have oxygen. There are 2 oxygen atoms. Oxygen is in group 16 on the periodic table, so each oxygen brings 6 valence electrons. So for that total from the oxygen is 12 valence electrons. We add the 12 to the 4, we have a total of 16 valence electrons to use. The next step is to connect the atoms by single bonds around a central atom. So let's put the carbon in the middle and the oxygens on the outside. Now you'll notice those single bonds are each 2 electrons, so that's 4 total electrons that I've used so far out of the total of 16. So I have 12 additional valence electrons. The next step is to fill the outside atoms with electrons to meet the octet rules. So let's place those 12 additional electrons as 2, 4, 6, 8, 10, 12. Now I've used all of my electrons, so I have a total of 16 valence electrons that show up either as pairs or within the bonds. So if it says use any remaining electrons to fill the octet on the central atom, I don't have any remaining electrons. So now I have a problem because carbon only is associated now with 4 electrons and it needs an octet of 8. So now we're going to use step 5 that says if the central atom does not have a full octet, what I'm going to do is share lone pairs from the outside atoms to form double or triple bonds. Now, if I grab one of these pairs of electrons from the oxygen, one of these lone pairs, and bring it in to make another bond, and I grab the same thing from the other oxygen, I grab a pair of electrons and I bring them in to make a double bond, what I can do is I can replace those electrons with lines, and now I have the carbon in the middle. It is associated with 4 bonds. Each bond is 2 electrons, so the carbon in the middle now has a full octet. The oxygen on the left has 2, 4, 6, 8, if you count each line as 2 electrons. So that oxygen on the left has a full octet, the oxygen on the right has a full octet. So now I have the Lewis structure, the line structure for a carbon dioxide molecule. And you'll notice that there are no lone pairs on the central atom. All I have on that central atom are bonds, so there's no loose lone pairs available on that central atom, which would affect the structure of carbon dioxide moving forwards. Our next example, let's take a look at SO3, sulfur trioxide. If we take a look at SO3, the first step is to count the valence electrons. So sulfur is in group 16. It's going to bring 6 valence electrons. Each of the 3 oxygen atoms also is going to bring 6 electrons, valence electrons, for a total of 18 for the oxygens. And 18 valence electrons plus 6 valence electrons gives me a total of 24 valence electrons available to form the structure of SO3. So now I'm going to connect atoms by single bonds around a central atom. I'm going to start with the sulfur in the middle and put 3 oxygens around connected with single bonds. That's already using 2, 4, 6 of the electrons out of the total of 24. That gives me 18 additional electrons to place in pairs around the outside atoms to make octets. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I've used all 24 electrons. Well, if you look at each of the oxygens, well, first of all, I don't have any remaining electrons to fill the octet on the central atom. But if you look at the oxygens, each of the oxygens is happy with a full octet, but the sulfur in the middle does not have a full octet. What that means is that I have to grab one of the lone pairs from one of the oxygens on the outside and bring it in to form a double bond at some point. So if I grabbed that pair of electrons and bring it in towards the sulfur, then I turn that pair of electrons into a line. So now I have a sulfur single bonded to the oxygen on the left, single bonded to the oxygen on the bottom, and double bonded to the oxygen on the right. Now, it wouldn't matter which oxygen atom you choose to move that pair of electrons from, because the oxygens, all of the oxygens still remain with a full octet. I just need one of those oxygens to be double bonded to the sulfur in order for sulfur to have its full octet. Now you'll notice if I look for lone pairs around the sulfur, there are no lone pairs around that central atom. Again, that's going to be important later on when you learn about atomic structure, molecular structures. Our next example, we will use CCl4, which is carbon tetrachloride. If I first count my valence electrons, I know that carbon is in group 14, so it's going to have 4 valence electrons. And then each of the chlorines from group 17 is going to bring 7 valence electrons. 7 times 4 is 28, giving me a total of 32 valence electrons to play with. So now we can arrange the atoms with single bonds around a central atom. Let me put the carbon in the center. Carbon is nearly always going to be in the center. And so now I've used 2, 4, 6, 8 of my total 32 electrons. So now I'm going to distribute the remaining electrons around the outside atoms to fill the octet rule. So that's another 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now that makes up the total 32 electrons that I had available. The next step would be to use any remaining electrons to fill the octet of the central atom, but I don't have any additional electrons, and the central atom already has a full octet. So what that means is that this structure for CCl4 is going to be complete. And again, if I look at the central atom, there are no lone pairs on that central carbon atom. All I have is bonds. I don't have lone pairs of electrons on that central atom. Our next example will be NH3, ammonia. If I count the valence electrons, step 1, what I'm going to see is that nitrogen comes from group 15, so it brings 5 valence electrons. Each hydrogen brings only 1 valence electron, so a total of 3 valence electrons from the 3 hydrogen atoms, and 5 plus 3 gives me 8 valence electrons to play with. Next, I connect the atoms by single bonds around a central atom. So if I put the nitrogen in the middle and connect it with single bonds to 3 hydrogens, that's 2, 4, 6 electrons so far. Now I'm going to fill the outside atoms with electrons to meet the octet rule. But since H can only have 2 electrons, the hydrogens are already complete with a full octet for the hydrogen, which in hydrogen's case, octet means 2. So the hydrogens are already full. Now I can go and use the remaining 2 electrons and put them as a pair around the central atom to complete the octet. So now I've used all my electrons. I've used all 8 valence electrons. I see that each hydrogen is associated with 2 electrons, which is good. And the central atom does have a full octet, so I don't need to share any lone pairs. I don't have lone pairs to share anyway. So this is going to be the structure of NH3 because each atom has satisfied the octet rule. Now, if you look for lone pairs, you'll notice that there is a pair of unbonded electrons around that central atom. So there is one lone pair on the central atom. Next example, we'll use the ion, the nitrate ion, NO3, with a -1 charge. In this case, if we count the valence electrons, the nitrogen, atom of nitrogen, is going to bring 5 valence electrons. Each of the 3 oxygens is going to bring 6 valence electrons for a total of 18. But then since I have that -1 charge, that means I have 1 additional valence electron to play with. So the total number of valence electrons is going to be 24. Hint, if you're counting valence electrons and you get an odd number, you know that something is wrong because you're always going to have the electrons in pairs. So now I'm going to connect the atoms by single bonds around a central atom. So let's put a nitrogen in the middle of 3 oxygens. So now I've used 2, 4, 6 out of my total 24 electrons. That means I have 18 electrons left. So now I'm going to fill the outer atoms with electrons to meet the octet rule. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. So now I've used all of my electrons. It says use any remaining electrons to fill the octet on the central atom, but I don't have any remaining electrons. I've used all 24 valence electrons. So now I have to go to the next step, and that is if the central atom does not have a full octet, which this nitrogen doesn't, it only has 2, 4, 6 electrons from the 3 bonds, I have to pull one of the lone pairs from the outside oxygen atoms and pull it in to make another bond with the nitrogen. So I'm going to share this pair of electrons in with the nitrogen to form another bond. And so now I have nitrogen double bonded to an oxygen and single bonded to each other oxygen. Now the total charge on this we've already determined is going to be a -1 charge because that ion has a -1 charge. And then you'll see that that central atom does not have any lone pairs. So I have no lone pairs on that central atom. The central atom is only bonding pairs of electrons. So there are no lone pairs on that central nitrogen. Now that you've seen how to draw Lewis structures, the next skill is to be able to identify, when given a Lewis structure, when given a line structure, to determine whether or not that structure is correctly drawn. So let's take a look at 3 different things that will help you evaluate whether or not the structure is correct. The first thing is we want to know if every atom drawn is going to meet the octet rule. Does each hydrogen have 2 electrons? Does each of the other atoms have a total of 8 electrons available, meeting the octet rule? The second thing is the total number of valence electrons correct. Have I brought in all of the electrons? Have they all been accounted for? And then are each of the electrons showing up in pairs, either as a lone pair on one of the outside or central atom, or in a pair shown as a bond, as a line. So each line is a pair of electrons. So let's take a look at selenium with 2 hydrogens, SeH2. Now, if I take a look at the selenium and I want to know if the atoms are meeting the octet rule, the selenium has 2, 4, 6, 8. If I take a look at each bond as 2 electrons, then I'm counting 8 electrons that the selenium is associated with. So that selenium is meeting the octet rule. However, if I look at the hydrogens, each hydrogen has a double bond, which is impossible for hydrogen because that would be 4 electrons. And we know that a hydrogen can only handle 2 electrons in its octet. So this means that clearly these atoms are not meeting the octet rule because there are too many electrons for the hydrogen. What about the total number of valence electrons? If we take a look at that, I've already put a check mark there, but we know that selenium comes from group 16. It brings 6 valence electrons, and each hydrogen brings 1. So that's a total of 8 electrons. And if we look, we have 4 bonds. Each bond is 2 electrons. So indeed, the total number of valence electrons in this case is correct. And are the electrons showing up in pairs? Well, each electron is showing up in a bond, and so each bond is a pair of electrons. So that's 1, 2, 3, 4 pairs of electrons. So it does meet that criteria. But the atoms are not meeting the octet rule, so this is an incorrect structure. If we were to look at the correct structure, it turns out that it's going to have a selenium with 2 lone pairs around the central atom, as well as 2 bonds. So in this case, selenium meets the octet rule. Each hydrogen is associated with a single bond, and that's a pair of electrons. So that would be indeed the correct structure for SeH2. As another example, let's look at O3. Let's take a look at this example for ozone. Now here, are the atoms meeting the octet rule? Well, the oxygen on the left has 1, 2, 3 pairs, that's 2, 4, 6 electrons, and then that bond counts as another 2 electrons. So the oxygen on the left is seeing a total of 8 electrons. The oxygen on the middle has a pair, that's 2, and then 2 bonds, that's another 4, 6, but that's a total of only 6 electrons around that central atom. Now the oxygen on the right does have 8 electrons, but in this case, since that oxygen in the middle is only associated with 6 electrons, this means that the atoms are not meeting the octet rule, so that central oxygen does not have enough electrons. What about the total number of valence electrons? Well, each oxygen brings 6 electrons because it's from group 16 on the periodic table, so that's 18 electrons. If I counted these electrons, it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, indeed, the total number of valence electrons is correct. And if you look at all the electrons do show up in pairs. But since the atoms are not meeting the octet rule, this is an incorrect structure. The correct structure, what would happen is one of these pairs on one of the oxygens would have to move in to form a double bond, and then I would get the correct structure for O3. Our next example has phosphorus with 3 fluorines. So the first question is, are the atoms meeting the octet rule? Well, if I look at each of the fluorines, they have 2, 4, 6 electrons spread around them in 3 pairs, and then each fluorine also has a bond. So this fluorine would count as a total of 8 electrons. This fluorine has 8 electrons. This fluorine has 8 electrons, so all of that is good. But if I look at the phosphorus, then the phosphorus only has 2, 4, 6 electrons. So this means that I have not met the octet rule because there's not enough electrons on that central phosphorus. What about the total number of valence electrons? Well, fluorine is in the 17th column. That means each fluorine has 7 valence electrons that it's bringing. And the phosphorus is in column 15, so it brings 5. 7 times 3 is 21, plus another 5 is 26. So let's count these. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. It turns out I don't have enough valence electrons total. There should be 26, but I only have drawn 24. So there's not enough total electrons, valence electrons. And then are the electrons in pairs? Yes, every electron is shown somehow associated in a pair. So the electrons are in pairs. So again, I have an incorrect structure. It turns out that if I bring in that extra pair of electrons that should be there, they can go around the central atom, and then the phosphorus would have a lone pair. So now the phosphorus would have its 8 valence electrons that it requires to fulfill the octet rule. So this would be the correct structure for PF4. Here's a structure for N2O. Let's see if this meets all of the rules. Are the atoms meeting the octet rule? Well, if I look at the nitrogen on the left, I've got 2, 4, 6, 7. I've only got 7 electrons on that nitrogen on the left. The nitrogen on the middle, I've got 2, 4, 5, 6, 7. I've got 7 electrons on the nitrogen in the middle, and then the oxygen has 2, 4, 6, 8. So the oxygen's good, but the nitrogens are not going to be meeting the octet rule. They don't have enough electrons. What about the total number of valence electrons? If you look at the periodic table, you see that oxygen brings 6 and each nitrogen brings 5. So that's a total of 16 electrons. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, there are the correct number of total valence electrons. And then are the electrons in pairs? Well, in this case, no, the electrons are not in pairs. I've got a single electron on each nitrogen, and that can't happen. All the electrons must be paired. It turns out that the correct structure for N2O is going to be a nitrogen triple bonded to another nitrogen and then single bonded to an oxygen. According to the rules we used before, there are actually 3 different structures you could draw, and there's some further advanced chemistry to decide that this is actually the correct of the 3 possibilities. But at this point, you can see that this structure would indeed match the rules that we have. So this would be a valid structure, and so would the other 2, but this one uses some more advanced chemistry to figure out exactly where the triple bond is. But this would be an example of a correct structure. Next, we have silicon with 4 chlorine, silicon tetrachloride. So let's see if this meets the octet rule. Well, if I count the electrons around this chlorine, each pair is 2, so that's 2, 4, 6. But then 2 bonds is going to be 7, 8, 9, 10. So this chlorine has 10 electrons. The chlorine on the top and the right and the bottom each have 10 electrons. That's not good because that's not an octet. And then if you look at the silicon in the middle, if each bond is 2 electrons, that's a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons around the central silicon, which can't happen. So clearly, I have too many electrons on every atom. I'm not meeting the octet rule. What about the total number of valence electrons? Well, silicon is in group 14. It brings 4 valence electrons. And then each chlorine brings 7, so that's 7 times 4, that's going to be 28. So I've got 29, 30, 31, 32. I've got a total of 32 electrons that I should have. If I count them, I've got actually 40 electrons, so I do not have the right number of valence electrons. And then are the electrons in pairs? Well, in this case, yes, indeed, they are. Now, if I were to draw the correct structure, it turns out that I only need single bonds between each silicon and the chlorines, and this would have the correct number of valence electrons, and each atom would meet the octet rule. So that would be a correct structure for silicon tetrachloride. So let's see if we've met the objectives. Can you count the total number of valence electrons that should be in a molecule? I hope so. Looking at the periodic table, identifying the valence electrons, and multiplying by the number of each atom, we now can count the number of valence electrons that should be in a molecule. We also can identify when a line structure meets or violates the octet rule, so we've been doing that over several examples. We also can count the number of lone pairs on a central atom, and we saw that the bonding pairs are not counted as lone pairs, but occasionally we will have lone pairs showing up around that central atom. And finally, we can identify when the line structure has the correct number of valence electrons by counting the total number of electrons that should be in the molecule. So I hope this was useful to you, and we'll see you again soon.